students, now let us calculate the force experienced by a rectangular current carrying loop in a uniform magnetic field. Okay, so what we have is we have a rectangular current carrying loop. So I will take an ideal rectangle A, B, C, D, which is placed in a uniform magnetic field. Okay, so this is north pole and this is south pole, and magnetic field is going from north pole to south pole. So the current in the loop is from A to B, from B to C, and C to D, and D to A. It is circulating like this. In fact, you cannot have this kind of system. You will have some more line here, but I am just considering a complete an ideal rectangle. So this is our system. Now this arrow is area vector. What does this mean is, okay, so this is the arm BC and this is the magnetic field, and between the magnetic field and the arm BC the angle is my phi. Okay, so it is like this. So this is my rectangular loop. It is something like tilted, and this is my magnetic field. Okay, and the angle between this BC and this magnetic field here is my, what is this, phi. Okay, so this angle is my phi. At the same time I have an area vector which is perpendicular to the area of this rectangle like this. Okay, so what this means is, this is my area vector. It is always perpendicular from here, from here, from here. So this is my area vector and this is my magnetic field. Okay, so to explain this I will give you one example like this. So let me give you this kind of thing. So this is my BC and this is my plane of the rectangle, and from the rectangle this is my area vector which is always perpendicular. Okay, area vector is always perpendicular from this plane. At this time this nip represents the magnetic field. This is my magnetic field, this is BC, and the angle between this magnetic field, okay, the angle between this magnetic field and this BC is here phi. So this is my phi, and the angle between this magnetic field and this area vector here is theta. Okay, so this is my theta, this is my phi. Okay, now if you add this plus this, you will get how much? 90 degree. Okay, which is a later part. So this is how it look like. Now let me whenever I place a current carrying conductor in a uniform magnetic field, it will experience a force we have done in the last lecture, and that force is F equals to ILV, IL cross of B, and which is ILV sine of theta, and sine theta is angle between the length vector and B vector. Okay, so similarly let me find the force on the arm AB. Okay, force on arm AB will be how much? Current is I and length, this is AB. So let this AB, okay, this AB is length L, and this BC has got the breadth B. Okay, so length is the length of the wire which is experiencing a force. Now this AB will experience a force, and from this I will get length, and let the magnetic field be this B vector. So this is my magnetic field, and there will be sine of theta. So what is theta? Is the angle between length and the magnetic field. Here this is the length element and this is the magnetic field. What is the angle? How much is angle? It is 90 degree. This is magnetic field and this is my current, isn't it? This is magnetic field and this is length. How much is the angle? Now can you see this? Magnetic field and length, it is 90 degree. So this will become 90 degree and this will become 1. So this will be equal to ILB. Okay, so this got the force, and this force the direction, let us find the direction of force is given by Fleming's left hand rule. Okay, so Fleming's left hand rule, it is given by Fleming's left hand rule. So if you see here, this is my Fleming's left hand rule. Father, mother, child, force, current, and father, mother, child, force, magnetic field, and the current. So here, where is current going? Current is going in this direction, and magnetic field is going in this direction from north pole to south pole. So this is magnetic field, this is going current, and force is going inside the board, isn't it? Inside the board, like this. Okay, current above, magnetic field, and force inside. So here what I can write is the force on the arm is going like this. So this is my force vector A, B. Okay, from each and every point. From here also force will go inside. Okay, from here also force is going inside. Now let me go to the force of on the arm DC. Okay, let me go to the force on DC. Again, I, length is same, L, B is same, and sine 90 degree, isn't it? Why sine 90 degree? Because current is going downward and magnetic field is going in that way. Okay, so like this. So this is my current and this is my magnetic field here, because magnetic field is going in this direction, current is going downward, so angle is 90 degree. So this is again what? 1, and this will become again ILB. It means that FAB is equal to FDC. Okay, from this, and let me go to the direction. So again, for the direction, what I need? Fleming's left hand rule. Magnetic field going where? From north pole to south pole. This is magnetic field. Current is going where? Down, and force is going towards us. So magnetic field this way, current that way, and force is coming out from the board. So at this point, I will have what? I will have this force, and this is my F on DC. Now tell me, are they opposite? Are they opposite or not? Yes. From this, the force is going inside like this. Okay? And from here, the force is coming outward. Force going inside, from here going inside, from there coming out. So force are equal and opposite. Okay? So to denote equal and opposite, I will put the negative sign. So it means that this arm will go inside and this arm will come outside. What will happen then? This arm will go inside and this one arm will come outside. Then it will give a rotation which is called torque. Okay. So what about the forces on BC and AD? Okay. On BC, this force will go in this direction. So this is the force, that will be force DC. Here the force will go downward. So this is force AD. What is this? Not DC, this is BC. Okay. BC. Are they equal and opposite? Yes, equal and opposite, and they are acting in the same line. It means that one force is going upward, one force is going downward, equal and opposite. Will they do anything? Nothing. It will not pull downward, it will also not pull downward, because they are in opposite direction. But not like this. It is going this side. Okay? यह यहाँ से इधर आ रहा है और ये यहाँ से बाहर निकल रहा है. Okay? So यहाँ क्या होगा? An opposite line of action is different. Line of action is different. Okay, what is different? Line of action. What do you mean by line of action? See, if you have this force, if it is coming towards me, and again if another force goes out from this side, then the forces will be looking like this. At this time, this arm will not move, because one force is coming towards me, one force is going towards you. So there will be no force, net force, because line of action is same. But if you do like this, your force, this force is coming this side and this force is going that side. What will happen? This will pull that way and this will pull this way. Okay, so this will rotate. But here, this and this. So what happens? There will be no force because it is going that way and it is going that way, and the line of action is same because the line of action is this one. In this line it is going that way, in this line it is also going that way. Okay, so it will cancel. So thus therefore it gives torque. It gives torque. But you have to write this. But F A B C and F A D are equal and opposite, acting in the same line of action. Therefore net force is equal to 0. Okay, so this will go upside, this will go downward, and they are acting in the same line, so they will cancel. The net force will become 0. But if you see this one, force AB and force DC here, they are equal and opposite, and line of action is different. Line of action is just right, and line of action is different. So therefore it gives torque. So it means that it will pull that way, it will pull that way, and it will give a torque. Okay, so now what we need to do? We need to do the derivation of torque. Okay, so let me go to the torque. So how much is the force we got? The force is ILB, isn't it? So because both the forces are equal. Okay. So force, we got force AB is equal to force DC, which is equal to ILB and opposite. Okay, and it will give a torque. So we know therefore the torque tau is equal to force into perpendicular distance between the two forces. Okay, so this is my perpendicular distance, okay, between the two forces. One force is this, another force is this. So I want to find this distance. Now if I shift it here, and let me write this as B dash. So B dash will be equal to this distance, okay? And I want the perpendicular distance between this and this. And the perpendicular distance, this is equal to this, isn't it? This is also, this is my B dash, isn't it? And this is also B dash. And this is my 90 degree. Now, if this is phi, then this will also become phi. Why? Because see here, this is magnetic field and this is something like this, and if it is phi and you draw a parallel line with this, okay, this is B dash, and this will also become phi. This is phi and this is also phi, because this line and this line are equal, parallel. So then I want to find the perpendicular distance. So this will be, what is my force? This will be ILB into what is my perpendicular distance is B dash. Okay. So how to find B dash? So this is my B dash, and this is my phi, and this is my perpendicular. I will find it from here. So if this is 90, then this will become hypotenuse. If this is phi and this is 90 angle and 90 degree, this will become base, and this is my perpendicular. So I want to find base, isn't it? So if you use cos theta, I will get cos theta is equal to B by H cosle pokera here. So I want to find base, then this will become H cos theta is equal to base. Implies this, how much is H? Hypotenuse is BC and cos of theta. Not cos theta, here it will become cos phi. Why? Because this is my phi, okay? Cos of phi will be B dash. So I want to find B dash. I got this one. Now what is B and C? B, C is my small letter b. So I will write this is B cos of phi is equal to B dash. So here I will write this is ILB into B cos phi cos phi. So this is my torque. Now if you see here, there is length into breadth, isn't it? This is length and this is breadth. Length into breadth is my area. Okay, so this I can write I, then A B cos phi. That is my torque. Now we are almost done. Now let me go to the some part of it. Okay. So this is almost done. Now if you see here, if it is like this, okay, and this is my B, C, and this is my magnetic field, and this is my phi. Okay. Now from this I have drawn a perpendicular A vector with the angle theta. So how much is this angle? This angle is 90 degree, isn't it? Okay, because I want to change this cos phi. So it is like this. This is area vector and this is magnetic. So this is magnetic field, this is area vector, and this is BC and magnetic field. Angle between BC and the magnetic field is my, this angle is my phi, and angle between this area vector and this magnetic field, this is my theta. It means that this angle plus this angle will give me what? 90 degree. Okay, because this is all, this area vector is always perpendicular. So phi plus theta is equal to 90 degree. Okay, so here from geometry, okay, from geometry, what I can write? Phi plus of theta is equal to 90 degree. Okay, this phi plus theta is equal to 90 degree, and I want to find phi. Therefore, this phi will be equal to 90 degree minus theta. This theta will go that side. So now what happens is, okay, now I can write, or this torque tau is equal to, there is I, this is area, this is magnetic field, and this will become cos 90 degree minus theta, because phi is equal to 90 minus theta. So then what? Then we know cos 90 minus A is equal to sin A. Okay. So therefore torque will be IAB cos 90 minus theta. Cos 90 minus theta is sin theta using this. So this is the net torque on the rectangular loop when placed in a uniform magnetic field. Now again I can write this torque equal to I area vector into B vector. Why? Because not B vector, yes, B vector. This is area, this is magnetic field. Because if you have A vector cross B vector will give me AB sine of theta, isn't it? AB sine theta, AB sine theta, so A cross B. So this is in vector form. So now the net torque is tau equals to IAB sine of theta. Okay. So what you have to remember, what is A is the area of this rectangular loop and B is the magnetic field. Now if there are n number of turns of valve. Okay, if there are n number of turns, I have considered single one turn. If there are 10, 20, 50 and n numbers, then torque will be how much? Then the torque will be giving me n a b sine of theta. Okay, and here you have to remember theta is angle between what? This a vector and b vector. Okay, area vector and magnetic field vector is. So how to remember this? And okay, I is also there. I is also there. Okay, this I. So to remember this, just remember National Basketball Association of India. कैसे याद करना है? याद करना है national. Okay, National Basketball Association of India. Okay, that is National Basketball Association of India sin theta. So this is all about the torque. So the same result we are going to use whenever we do the galvanometer. Okay, so this is very simple. If you get any confusion, let me know. Thank you.